Hello physics students. Today we're going to talk about efficiency. Now when you use a device, any modern device, like maybe a washing machine to wash your clothes, your cell phone to send a text message, or your car to drive to school, what you're doing, or what the device is doing, is taking some kind of energy that you put into it and converting it into a kind of energy that you want out. Like for example, your car, you put the gasoline into the tank, and then it does work to get you to your destination. But efficiency is like a grade of how effective the device is at transferring the energy you give it to what you want out of the device. And you can calculate that with this basic formula. First of all, efficiency, I'm going to use the symbol capital E for efficiency. And the formula for calculating is the useful energy you get out of the device divided by the energy that you put in, the total energy, times 100%. So as I said, it's a percentage like a grade. Like you know, a 20% is bad. That's like an F. That would be a very inefficient device. That means it's only taking 20% of what you're putting in and giving you what you want out of the machine. Something that's 99% efficient, that's a good grade because 99% of the energy you put into the device, it gives you as what you want. Like for example, the car I mentioned, the efficiency would be the work output driving you down the road to your destination divided by the gas energy that you put into the tank or that it burned in the process times 100%. In the case of an oven, when you're cooking food, the heat into the food is what you want. You want the food to get hot so it cooks. So that's the useful energy. But you might, if the stove is electric, be getting a certain amount of electric energy out of the wall, times that by 100%. That's the percentage grade for the stove. And another example, a light bulb. Oh, so let me create a little pause here to allow you to catch up by copying these notes down. Okay, so one more example, a light bulb. What we're going to do is in this class, we're going to actually, in this video, we're going to determine the efficiency of an old style incandescent light bulb, not an LED bulb or a fluorescent bulb, one that has a filament and produces light. So like the really old fashioned kind of lights, not the modern. And what you're trying to get out of a light bulb is obviously light energy. You flip the switch on so that you can see what's in the room. And so the light energy is the useful energy, but it takes a certain amount of energy out of the wall, multiply that by 100%, you'll get the efficiency of the light bulb. Now I'm going to do, as I said, a little experiment, but before I jump into the experiment, I just want to do a little diagram to, or create this little diagram, show you this diagram, to talk more about the energy dynamics that are happening in a light bulb. What happens is the electrical energy comes out of the wall, and yes, some of it becomes light energy. But there's also heat. When you grab these old bulbs after they've been on, you could burn yourself. You probably know that if you've tried to change a light bulb that just went out. So what are we talking about its efficiency? Let's suppose 10 joules of energy comes out of the wall, and 9 joules of it becomes light energy. Obviously, the heat is 1 joule because energy has to be conserved for the light bulb. So it took in 10 joules, 9 and 1 come out as different forms, so 10 comes out. 10 went in, 10 came out, energy conserved. This bulb then, the efficiency would be 9 divided by 10, or 0.9, times 100 is 90% efficient. That would be a good light bulb, you know, like an A grade. Or you could have, just as a hypothetical, suppose 10 joules was consumed out of the outlet, but only 2 joules went to light energy. Well, obviously went out the other, out as heat is the difference between the two, 8 joules. And so energy is conserved 10 before, 10 after. And the efficiency of the light bulb would be 2 joules over 10 joules, or 0.2, times 100%. It's only 20% efficient. Bad bulb, right? That's like an F. So we're going to grade this light bulb in an experiment, as I said, but as I'm going to explain in just a second, we can find the light energy if we didn't know what it was by, if we didn't know that, we could just take this minus that, and we know that that's 2, right? So that's what this is saying. The light energy over here is the difference between these two, and you'll have the light energy. All right, so now I'm going to reconfigure the camera so we could do our little experiment to figure out the efficiency of this light bulb. Now we're going to observe the energy dynamics I just talked about on the board for this real light bulb. This bulb is connected to an outlet down here through these wires, and what's going to happen is the electrical energy is going to come out of the outlet and it's going to go into the bulb. And the bulb with that electrical energy will obviously create light, but it also creates heat as a byproduct. This bulb will get very hot as time goes on. So what we want to do, as I said, measure the efficiency of this bulb. So the higher percentage of light energy compared to the electrical energy, the more efficient it is. The lower the percentage, in other words, the more heat this produces, the less efficient it is. In order to actually calculate the efficiency, we need the electrical energy in from the wall outlet and the light energy. So first, the electrical energy. In order to determine the electrical energy, in the reference table of our course, you can see that we have to measure the electrical properties of this bulb. Like, for example, what I'm going to do is measure the voltage and the current going into the light bulb. First, the voltage. I've got a meter here, a multimeter, which I have configured to measure voltage, so that makes this now a voltmeter. And what I'm going to do is turn this on, and I'm going to stick these right into the outlet. So again, I want to say that a lot of this stuff you shouldn't be doing at home unless you have training, extra training, because I am sticking these in to the outlet. There is a possibility for electrocution, so you don't want to do this unless you really know what you're doing. But I'm going to stick these in to register or measure the voltage of this wall outlet, and it's about 121.6 or yeah, it looks like 121.6 is where it's resting most. So there's the voltage. I will write that down for later use. 121.6. Now, the current, how will I measure that? What I've done is I've modified an extension cord. Again, you're not going to be doing something like this at home because of the danger. I've cut it so that it can plug into this meter and measure the current in this light bulb. And so what I'm going to do is plug this cut extension cord into this outlet here. Let's see, what's a better angle? Maybe like this. All right, and then at this end, I'm going to plug in my light bulb. Now when I turn this dial to read amps, it's now this multimeter becomes an ammeter. And when I turn this on, you can see that we get the current registered here. You saw go away from 0. So I'm going to have I have the voltage, I'm going to have the current, which I'll record while I'm doing my experiment, and I'm also going to measure the time, and from those we can calculate the electrical energy that came out of the outlet. One thing that we need, the denominator of our efficiency calculation. Now, what about the light energy? I mentioned on the board that it's difficult to capture the light and to quantify it. So what we're going to do is concentrate on the heat instead. So I'm going to set up the experiment, and I won't tell you what I'm going to do yet. You're going to see what I'm going to do. You might find a little surprising. So first thing I'm going to do is take this glass beaker, and I'm going to measure its mass, 160 grams. Next, what I'm going to do, yes, that is water. I'm going to put some water in this beaker. So, I need this the right amount here. That looks good. And I'll put this on here, and I get 335 grams. That's the glass and the water. So if I want to know the mass of just the water, I've got to subtract those 335 minus the 160, and that gives me 175 grams of just water. I'm also going to need the initial temperature of the water, which looks like we're down around 12.5 degrees. You probably can't see that on the screen, but 12.5 degrees Celsius is the initial temperature of the water. Now, yes, I am really going to submerge a light bulb into this water and turn it on. Again, this is why I'm going to say, or I should say, I'll say once again, do not try this at home because it's not 100% safe. It's relatively safe. I'll tell you why I can get away with this is because I put the bulb in the water when it was cold, and when I turn it on, the water is going to keep the glass an even temperature. If I turned it on and then tried to put it in, I'd be taking hot glass and putting it into a cold water, and that would create a shattering effect. All right, so there, I'm ready to go. And what I'm going to do is turn this circuit on and start the timer, so I will be measuring the time and ultimately the temperature increase in the circuit. So, ready, set, go. All right, so what's happening now is energy-wise, the light energy is free to escape through the glass and the water, but the heat is not. It's captured by the water and the glass. So I'm trapping the heat energy. I'll be able to calculate them from the measurements of the temperature increase, and that'll ultimately allow me to get the efficiency. Now, I also need the current, as I mentioned, 1.24 amps going to that light bulb. So I will write that down, 1.2, looks like 1.23 amps now, okay. And now I'm just gonna wait a couple minutes and sort of agitate this water so that, you know, it stays equal temperature all around this glass of the bulb, so it'll help it not shatter. Approaching 2.5 minutes. So what I'll do is stop the timer and shut off the electricity at the same time. Ready, set, go. Okay, 2 minutes and 36 seconds. Well, we could round up to 2 minutes and 37 seconds. So let me write that down, which is 2 minutes is 120 seconds plus another 37 is 157 seconds is the time. All right, now I need the final temperature of this water. Degrees Celsius. Let's call it 30 degrees Celsius. You probably can't see that, but I'll write it down as 30 degrees Celsius. All right, we have all the data we need to calculate the efficiency of this light bulb. So let's go back to the board. So I've transferred the data that I collected onto the board here. And for the total energy coming out of the wall outlet, I measured the voltage, the current, and the time that the bulb was on. To measure the heat energy that was absorbed in the water and the glass, I measured the mass of the water in grams, the mass of the glass in grams, the initial and final temperature of the water, and then the delta T, the change in temperature by subtracting those two. So I'll create a pause to give you a chance to copy these down. All right, now we need to analyze. So the first thing we're going to do is calculate the total energy, the electrical energy that came out of the wall. And to do that, we could use one of the formulas on our Regents reference table. So I am in the electricity section here, which you should be familiar with by now. And down here, I see that work, which is electrical energy, and I see a bunch of formulas here. Since I have the current and voltage, I'm going to use this. Voltage times current times time. So that's what I'm going to use to get the electrical energy, the energy that came out of the wall outlet. So they had a VIT, I wrote it IVT, same formula. Current, voltage, time from here. Punch that on a calculator, get 23,482 joules of electrical energy came out of the wall. Now let's calculate the heat absorbed by the water and the glass. So in order to do that, I have to use a formula that's not in the reference table. It's not part of the curriculum. Remember I said in the energy unit, later in the year, we're going to need that formula for the heat absorbed by something. So now we're going to use it. So this is what we call the specific heat. It's a capital C. This is the mass of the substance in grams and the change in temperature. And we have to include the heat that the water absorbed and the heat that the glass absorbed because they both warmed up as a result of the light bulb on. So this C I can look up in a book. I have a book here, an old book, okay, so probably from like the 1970s, but it has the data for water and glass, the specific heat. The specific heat of water, C, is 4.16 joules per gram per degree Celsius. The mass of the water was 175 grams, and the change in temperature was 17.5. I used the same formula, but now I need the specific heat for the glass, which is 0.83 joules per gram per degree Celsius, and the mass was 160 grams, and the temperature change was the same as the water because they were in contact. So now I just need to punch that in on a calculator. So let me make some room here for the result. But if you need a moment to catch up, I'll create a pause so you could copy this down. All right, what did that come out to be? If you hit that on a calculator, you get 15,064 joules. So heat is 15,064 joules. And right away you could see it's more than half. This bulb is very inefficient. But let's continue on and get the actual value of the efficiency. So now to get the light energy, that's what we need for the formula. As I said in this over here when I erased this, that I could take the total and subtract off the heat, and that will be the light energy. If you go back to that diagram I had over here, you'll see again the logic behind that. So the total was 23,482 joules. The heat energy we just figured out was 15,064 joules. Punch that on a calculator and you get 8,418. All right. That's the useful energy. That's why we're turning this bulb on. We want the room to get brighter. We want the light energy. So this is the grade. How much of this is what percentage is of the original? Well, we can calculate by using that formula. Again, it will be the light energy over the total energy coming out of the wall times 100%. Let me make some room for that final calculation. And so we can say the light energy is 8,418. The total coming out of the wall was 23,482 times 100%. Punch that on a calculator, and you get 35.8. F. All right, before I comment, let me create a pause to give you a chance to copy these notes down if you need some extra time. So, this light bulb, 35% of the energy goes to light, or 36. 64% of the energy coming out of the wall goes to creating heat. So very, very inefficient. And you know, you hear a lot of people talking about these things, and they don't really have the science down behind it. People say they want these bulbs because the new LEDs are terrible. They say, so, you know, they have all kinds of reasons why they think the LEDs are terrible. But just think about this. If all appliances were this inefficient, imagine you spend, I'll make up a number, $200 on electricity in a month to do all your things. Wash your clothes, you know, watch TV, work on your computer. And then let's assume that everything is 35% efficient. So that would be $70 of the $200 went to actually doing useful things. $130 out of $200 went to just waste. And it's worse than that, because think about this light bulb in the summer heats up your house, and then you get doubly hit, because what happens is your air conditioner turns on. So it makes the and now you're consuming more on that end. So inefficiency is a terrible thing, and it's really bad for a lot of appliances. So up until a few years ago, that's just what people accepted from appliances. If you take a gasoline motor, it's even worse when you have a traditional car, not a hybrid, but like just a regular old gas car. I don't know what it might be like 90% of your gas money goes to just heat loss. So imagine you have a $100 gas bill for a week, only $10 of that was what took you from point A to point B all week. $90 of that just went to waste, right? So you can really see, for us, the consumers, what we really want is things to be efficient. We don't want to waste money. But if you're selling the energy, then you probably might want things to be a little more inefficient to, maybe, some utility companies do push efficiency, which is great. But interesting calculation, the efficiency of a light bulb, the efficiency of anything, if you go back in your notes, it's the useful energy you get out of the device divided by the total that you're paying for, times 100%, and it's a grade of how good it is at converting the energy to what you want. And also, we used, nice in this topic, I erased it, but all our circuitry stuff, current, voltage, time, and we were able to get electrical energy to figure out something very useful, the efficiency of an old-fashioned light bulb. All right, so I hope you enjoyed the physics. I hope you were surprised, and maybe it'll motivate you to think more about these things in your life when it's your turn to set up your house or your apartment, and you'll be a little bit more wise about looking for efficiency. I hope that happened too. I hope you enjoyed the video, and I'll see you in the next physics video.